Kia ora and welcome to this video on question 5 of the 2020 Scholl Calc exam. There's quite a bit involved in this question. There are 4 parts. The first is a fairly reasonable trig identity question that has a link to complex numbers. The second one has an integral in it that is very similar to question 4 of this paper, which is in an earlier video I've recorded, in which case you can use integration by parts to do it, or use the hint linking to complex numbers, which we're going to do because I think that's the intention of the question. The third problem is a complex numbers question similar to an excellence problem in the NCEA standard. We're going to look at it in an algebraic and geometric manner. And then the fourth question is an absolute humdinger of a system of equations, one that I tried about 5 different ways of rearrangement and elimination before I realised that there was a small little trick in the problem. Not easy to spot, but once you notice it, it's a beautiful question. Positioned question 5D because it's actually quite hard, even though on the surface it looks fairly reasonable. Anyways, let's kick into the first part. So we've got this formula that we may have seen before, Euler's formula, that connects the complex number form and the polar form that we're familiar with from NCA, cis theta, to E, which is Euler's constant. So you actually don't need to know the first part, the e to the I theta part, to be able to find an expression for cos theta. And I'll just explain what I mean by that. If you have a complex number z, which we write in polar form as cos theta plus I sine theta, and we're talking here about a complex number that has a modulus of 1, so we don't write r cis theta, it's just 1 cis theta. Then the conjugate of z, is cos theta minus I sine theta, which is actually the same as cos minus theta plus I sine minus theta. Okay, so the conjugate, there's 2 ways of thinking about a complex number and its conjugate. We have a real axis here and an imaginary axis. If we have a complex number z, which is some distance away from the origin at an angle theta, the conjugate has exactly the same real part, but it has the negative imaginary part. So it would be down underneath, or a reflection in the x-axis. So its argument would be negative theta. And the reason for that is cos theta and cos minus theta are exactly the same, because cosine is an even function. And sine theta, if we want the sine of minus theta, we change the sign there. The negative becomes a plus. And sine is an odd function, so the sine of some value is the negative of the sine of the negative of that value. That was a bit of a mouthful, but if you look at a sine graph and you pick any old random value of x, say for example there, then if you go to negative x, the value you get will be the negative of the value you got if you subbed an x. I hope that makes sense. Okay, so with those complex numbers, z and its conjugate, if you add z and its conjugate together, the imaginary parts cancel and you get 2 cos theta. And then if we divide by 2, we get cos theta. Z plus its conjugate divided by 2. And so we can see that with the identity that we've been given, e to the I theta. If we write e to the minus I theta, that's cos theta minus I sine theta, the conjugate. And then when we add them and divide by 2, we get cosine. Okay, so to summarize that one, we would write e to the I theta is cos theta plus I sine theta, e to the minus I theta, so in other words change the thetas to negative thetas, it's cos negative theta plus I sine negative theta, which is the same as cos theta minus I sine theta, and then adding, if we add these 2 things together, the imaginary stuff disappears and we get 2 cos theta, and then if we divide by 2, then we get our proof. Awesome. So that's a nice start to the question. Part B with the sine cubed of theta, you can do a standard trigonometric approach in this question, because it's actually quite easy to look at the sine 3 theta bit. We've done this in a similar video as well, and go sine 3 theta is sine of 2 theta plus theta, and then use the compound angle formula on the formula sheet to expand it, and then use a double angle formula to get rid of the 2 thetas. So you can prove that using a trig identity approach, and I encourage you to do that. But the sort of purpose of this question is to connect the complex number e to the I theta to the cosine and sine parts, the real and imaginary parts. So if we do that, this question starts with the left-hand side of sine cubed theta. So the first question's kind of scaffolded at us to think about what cosine theta is. Now if we subtracted those equations instead of adding them, okay, so actually I'll come back to sine cubed theta in a sec, but if we took e to the I theta and we minused e to the minus I theta, the cosines would disappear. We'd get I sine theta take away negative I sine theta. We get 2i sine theta. And if we divide by 2i, that's our similar expression for sine of theta. Okay, so then from that we can cube it. Left-hand side, sine cubed theta, which is this whole thing cubed. 2i is just a constant, so when we cube that, we get 2i times 2i times 2i, which is 8i cubed, and I squared is negative 1, so 8i cubed is negative 8i. I'm going to need a little bit more room on this. So we'll go negative 1 over 8i. And then we need to expand e to the I theta minus e to the minus I theta, all cubed. Now, if you haven't seen binomial expansions before, that's an area of maths that I definitely recommend you look into, because we don't have to write out 3 brackets here. What we can do is think about what a plus b cubed is. If I wrote out 3 brackets, I'd get the same answer. It's just a little bit more tedious. And we get here is a cubed. The coefficient, of a cube is 1, 3, 3, 1. That comes from Pascal's triangle. A cubed, a squared, a, and a to the 0. And the other side, b cubed, b squared, b, and then b to the 0. And then plus, plus, plus. So that's how we expand a binomial really quickly. So for this one, we've got e to the I theta cubed plus 3e to the I theta squared times negative e to the minus I theta, and then 3e to the I theta, which is single power, times negative e to the minus I theta squared, and then we've got plus negative e to the minus I theta cubed. Okay, and the way that powers work when we're in brackets, some MCAT stuff there. We've got e to the 3i theta there. We've got the last term, which is e to the minus 3i theta. And then we've got common factors of 3. And if we multiply those terms that are after the 3's, the first one we get e to the 2i theta, and then we get e to the minus I theta, so multiplying those together is e to the I theta. And there's also a minus. Apologies, the factors are minus in that one. Do I want it that way around though? Yep, I do. So I go minus e to the I theta, and then the last term I haven't done that one there. E to the I theta times e to the minus 2 I theta. Add the powers, we get e to the negative I theta, and there's a minus in front of it. Okay, now it looks very similar to the formula that we started off with in the brackets there. Okay, so we already know from our right-hand side expression that we're trying to connect this to sines of, where is it? Right-hand side, we're looking for a sine of 3 theta, and we're looking for a sine of theta, but we've got some fractions, 3/4 and 1/4. So if I write this as minus 1 over 4i, so that I can distribute a 2 back into the brackets. And then this last one here is minus 3. I don't really need brackets there. What you should be able to notice, hopefully, is that first term in the brackets is sine of 3 theta, and the last term in the brackets is sine of theta. And it looks like we're wrong here, but we've got that I in the denominator at the start of the expression. So if we want to deal with that, we can times by I over I, and that will get rid of the I in the denominator. Oh, actually, my bad. A couple of lines earlier, I distributed a 2 into the expression, but if I actually really needed to put the I in there. I kind of forgot that sine of theta has an I in the denominator. Okay, so we're actually all good there. But I can get rid of the I on the outside. Brilliant. But if there was an I in the denominator and we needed to get it into the numerator, we could times by I over I. And I think that's enough to prove it. We've got 3 over 8 sine theta. And then we've got minus 1/4 sine 3 theta. Let's see, is that what we were proving? Ooh, 3/4. Why 3/4? Because I took the 2. My goodness, this is a lot of mistakes. Usually in class I'll be giving out lollies for this. It's always good with the right hand side that you're trying to prove, right? You know if you're wrong, and you can go find the error. Okay, now for the second part of this question, we've got an integral that involves cosine of x. We also have some information about how complex numbers and integrals kind of work. That this integral here works exactly as we'd expect it to. The reason being, we know that if we integrate e to the ax, then it's just the same thing divided by a. If a is a constant, we get a plus c, which I noticed that the exam has missed out. So if we have e to the 1 plus I times x, and we're integrating that, it's e to the 1 plus I x divided by 1 plus I. So it works exactly how we would expect it to work. So how does that hint apply? Well, we can replace the cosine x part of this expression with the cosine formula that we've already derived, and then integrate. And the thing I like about this question is it introduces you to a new way of integrating. We could do integration by parts, as I mentioned earlier, but we don't need to. So let's go integral of cosine x e to the x. We can replace the cosine x with our formula, which we got in part A, e to the I theta plus e to the minus I theta divided by 2. Except we're dealing with x's now. X is our variable, so we use x. there, and then I want all of that to be multiplied by e to the x. So we use our knowledge of our powers work. We can pull the half out the front of the integral. So I'm adding the powers. Ix plus x is I plus 1 times x. And then we've got negative ix plus x is 1 minus I times x. Okay, and we're integrating those two terms. So we use the hint. E to the I plus 1 stays the same, but we divide by I plus 1. And this one here stays the same as well. Divide by 1 minus I. And this looks, nothing like the expression we saw on question 4 when we did this problem in an earlier video. But to get it into that format, all we need to do is rationalise these things. So times by the conjugate of the denominator, top and bottom. So if I do that, so times by I minus 1. Well, it's actually 1 minus I, but it'll do the same. It'll have the same effect. And then do it with the other one, but times it by 1 plus I. Okay, so we have a half. The I minus 1 times I plus 1 on the denominator, it's a difference of two squares. So it's I squared plus I minus 1. And the I squared bit's negative 1 as well, so we get negative 2 in the denominator. And in the numerator, e to the I plus 1 x times I minus 1. And the other one we've got 1 minus I over 1 minus I times 1 plus I in the denominator, which becomes 2. And then numerator that. Okay, so it doesn't look like it, it doesn't look like we're expecting in terms of having trig functions in it, but that's where that formula we've already seen before comes in handy, because we have how can I explain this? We know that sine of theta is e to the I theta minus e to the negative I theta, all divided by 2i. That's something we've seen before as well. Okay, so if I pull an e to the x out of both of these expressions. So we've got an e to the x there, and we've got an e to the x there. So that comes out the front. Then we've got e to the ix left in the first term times I minus 1. And in the second term, we've got e to the minus ix left. And then we've almost got the sine theta thing appearing. If I want to get rid of this minus in the denominator of the first term, so it becomes a 2 as well. So make that a 2, then I just flip the I minus 1 bracket around. 1 minus I. Okay, and then I look at the first term of that one's e to the ix, and there's e to the minus ix there. So I've got e to the x over 2, e to the ix plus e to the minus ix all over 2. And then the stuff that I haven't dealt with yet, I've got a common factor of I. So I've got plus I and I have actually it's a common factor of minus I will work better for us. If I pull out minus I out of it, it's got e to the ix minus e to the negative ix all over 2. And then the first part, there's the cosine formula we've seen already, which we've already used in this integral in line 1. It's the cos theta equals e to the I theta plus e to the minus I theta over 2. So I use that formula for the first part. And the second part almost looks like the sine expression, it's just missing the I in the denominator. And as I was mentioning in the earlier problem we did, if I times the top and bottom of that second expression by I, then it's going to be I squared in the top, which will be negative 1, so that will turn that to a plus and get rid of the I, and then we'll have an I in the denominator. So times by I over I. Okay, so that there's e to the x over 2 cos x plus sine x, and then we also do need a plus c. Okay, so that there is the integral of that expression. Now that there is a lot more tedious, I think, than integration by parts, but it's quite nice that you can do that problem in that way. Okay, the third question that we've got, part C. Suppose z is a complex number with the modulus of 1, describe the locus of W. A standard approach to solving this problem would be algebraic. So if we start off with let z be a complex number with a modulus of z equals 1. Okay, that just means that if z is equal to x plus iy, you could use complex numbers as well. So you could start off with cos theta plus I sine theta, because we know its modulus is 1. But let's go real typical approach from an NCA student. Z equals x plus iy. But we also know that the modulus x squared plus y squared square rooted, we know that that equals 1. Okay, it means that z there is a distance of 1 away from the origin, and so it's real part and it's imaginary part. When we square them and add them, we get x squared plus y squared equals 1. Okay, and the complex number that we've been asked to consider is W, which is z plus I divided by I minus z. Okay, now two complex numbers when you are dividing, so z plus I is a complex number, I minus z is also, when you divide them, you want it you want to get it into a standard form like a plus bi, and we use conjugates to do that. But division's actually easier in polar form, so we're going to look at that in a sec. But we'll continue with this typical approach. So an NCA student normally would put x plus iy in there, and then x plus iy in there, and then you group the real parts together. So x is the only real part in the numerator. You've got y plus 1 all times I. In the denominator, the real term is negative x, and then there's an I minus iy, so 1 minus y all times I. Okay, then we're times by the conjugate, top and bottom. Conjugate of the denominator, negative x minus 1 minus yi. Do that on the top as well. So we're just timesing by 1 here. Denominator, I don't expand unnecessarily, but I know that when I take a complex number and times by its conjugate, it's like a difference of 2 squares. So the denominator becomes x squared minus, it's a squared minus b squared, but because of the I squared part, it's a squared plus b squared. So it's x squared plus 1 minus y squared. And then the numerator there's real terms if I take the x and times by minus x, or the y plus 1i and times by the minus 1 minus yi. So they're the real terms I get. So minus x squared, I do these ones first. Y plus 1 times 1 minus y, the I squared bit's -1, there's another negative, so plus y plus 1, 1 minus y, they're the real parts, and then plus I, we've got two imaginary parts that come from the other two multiplications, x times -1 minus y, oopsies, got my negative in the wrong place there, x times, well, -1 minus y is the same as y minus 1, so x times y minus 1, and then the last one, y plus 1i times -x minus x times y plus 1, and that all times I, so the i's out the front there. Okay, the numerator expands out. And the other bracket there simplifies a bit because the x, y's cancel. And then we use the fact that we know that x squared plus y squared equals 1. So this dude here is -1, and it cancels with the +1. So we've got no real part left. We've got minus 2x all divided by this stuff times I. So the result, W, if Z is a complex number with a modulus of 1, W comes out to be purely imaginary complex number with a real part that is 0. And it's defined for all values of x and y except if that denominator equals 0. And because it's a sum of two squares, it exists, which exists if and only if xy doesn't equal 0, 1. So what does that mean if xy does equal 0, 1? That would be z equals x plus iy equals I, if y was 1. So if z is equal to I, if you go back to that original expression, then you get division by 0. You get 2i divided by 0. So, of course, w doesn't exist for that case. But every other value of x and y generates something. And so what we've actually got is some real number times I. And I'll leave you to think about it, but the real number that's in front of the I can be any number between minus infinity and infinity, depending on what you choose for x and y. So the geometric interpretation of this is W is a complex number that lies on the y-axis in the argon plane. Alrighty, so there was an original restriction on what z could be, but w can be any complex number on that line. Okay, there is another solution in the marking schedule which involves bisectors. You can look at that if you're interested, but I've got a nice little diagram here to help us understand this, what we've just done geometrically. So I made this one earlier, it was a bit messy. But if you start off with a complex number z, as I've got here, and z is on the unit circle, it has a modulus of 1. Z plus I sits directly above z, just 1 unit above. So this length here is 1. That length is also 1. I minus z is a little bit tricky to think about. I first think about what minus z looks like. So if you take a real number and you take its negative, it's on the complete opposite side of the x-axis. But if you take a complex number and make it negative, you get the negative real and the negative imaginary part. So z starts here, minus z starts 180 degrees around the origin with a negative real and imaginary part. And then we add I to it to get I minus z, and that shifts it up by 1. It's just in the imaginary direction, so vertically. Okay, and then we've also got 1 there. So we've got two isosceles triangles here. Now, z was some complex number, it could be anywhere in the unit circle, so we could start with that angle theta. Z plus I, because it's further up, its argument is a little bit bigger, and I don't bother finding that angle alpha. I could use trigonometry to find it in terms of theta, but it's not necessary for this proof. Likewise, I minus z, well, that's even further around. But what we've got, there's a straight line there where, I guess this angle here, let's call it, I don't know, beta. This angle is also beta because we've got an isosceles triangle. And this angle here is also alpha, isosceles triangle. What you need to show is that the angle here is 90 degrees. Okay, it can be seen on the picture, but I'll leave you to fill in the details of why that's 90 degrees. And so when it said, like, tell us what W is doing, what was the actual wording of the question? Describe the locus of W. So W is equal to z plus I divided by I minus z. And I said that division is easier to think about in polar form. So z plus I is some complex number. I don't know, we'll say R1 cis theta 1 divided by R2 cis theta 2 as a denominator of a complex number as well. And when we divide complex numbers in polar form, we divide the moduli and we subtract the arguments. So theta 1, which is the argument of the first complex number, in my diagram that's this angle alpha plus theta, that's the new modulus. If I subtract the second argument, which is that plus another 90 degrees, if I can prove that that angle is 90, I get negative 90 when I subtract. And it depends on where you start z. If I start z in a different position, then I minus z will be on the other side, and that angle will be negative. So the negative 90 will become positive 90. So we're going to have plus or minus 90 degrees in that. And then the R1 over R2, well, R1, the modulus of z plus I is this length, and R2 is that length. And if I really wanted to know the value of it, I would have to use trigonometry and make a right angle triangle there, and R2 over R1 is the tan of this angle up there. But actually, I don't to solve this problem, I don't need to know what the value of R1 over R2 is. All I need to know is that it's a real number, because a modulus is always real, divided by another real number. So it's something like that. And cis of 90 degrees, or cis of negative 90 degrees, one of them's I, the other's negative I. So we've got plus or minus ki, some real number times I. In other words, it's purely imaginary. Okay, so the hard part of this proof is reasoning why this angle here is 90 degrees from the triangles that I drew. The easy part of the proof is knowing how complex numbers divide in polar form, rather than doing the whole conjugate thing, which is dividing in rectangular form. And those little tricks, the geometric tricks here, help with complex number scholarship problems a lot more than they do with NCA level 3 ones. Okay, this fourth system of equations is a very, very sneaky problem. And like I said earlier, I tried heaps of different rearrangements and wasn't getting anywhere. The key thing to notice is when you subtract, if we could just label these equations, equation 1, equation 2, and equation 3. If you go 2 minus 1, 2 minus 1 gives you y squared minus x squared, which is a difference of two squares, minus zx plus yz equals 1. It gives us the same thing on the right hand side as if we go 3 minus 2, just by the numbers that they've chosen. So the right hand side will be the same, it will be equal to 1, and this one we get z squared minus y squared minus xy plus zx. So if you just do a standard approach to this system, and you look at the first equation, and you make, make y the subject in terms of x and z, and then you dump it into the next equation, and you've got an equation with only x's and z's, and then you make x the subject of that and dump it into the other. It causes problems because you end up with like powers of 4, powers of like basically equations you can't rearrange and make the subject of. So, okay, how has this helped? The first equation, like I said, difference of two squares. We've got y minus x times y plus x there. And we've also got y minus x out of this stuff. So there's a common factor of y minus x. Okay, and we do the same thing for the second one, z minus y, z plus y. Common factor is z minus y. Okay, and there's an x plus y plus z there, in both of them, which must be the same. So the right hand side of 1 divided by that is the same. So we end up getting y minus x is the same as z minus y. And this is an arithmetic sequence, x, y, z form an arithmetic sequence. In other words, a linear pattern. So if we have x, y, and z are the three terms in this pattern, the difference between z minus y, some value d, which they use in the mark schedule, is the same as this distance here, d. What that means is that the y value in the middle is actually the mean, or the average of x and y and z. So y is equal to x plus y plus z all over 3. Leave you to think about why that is. And if we pick any of the equations, I choose equation 2 to be consistent with the mark schedule. Equation 2 is y squared minus zx equals 2. But z, well, that's just y plus some difference d, and x is y minus some difference d. So we've got y squared, take away y plus d, y minus d. The difference of two squares again, and the y squareds cancel. And the dy and the minus dy cancel. So we're just left with d squared equals 2. D is plus or minus root 2, depending on what order the sequence is, whether it's x, y, z, or z, y, x, in terms of increasing to decreasing. So we've got the d value is plus or minus root 2. And we had earlier that x plus y plus z, that came from this, the dude highlighted up here. So our final step to solving this is to realize that that distance d, which is actually just 1 over x plus y plus z, so we know that that's equal to root 2, which means that x plus y plus z equals plus or minus 1 over root 2. and therefore y is equal to plus or minus 1 over root 2, all divided by 3 from this equation. Okay. Once you've got the y value, there's two of them, you can substitute those back in, knowing that y minus x is equal to d and z minus y is equal to d. You can find the z value by adding root 2 or subtracting root 2 from the y value, and we can find the x value by subtracting or adding d to the y value. So I'll leave that detail out, but you can find x and z quite simply. So system of equations is a really mean one, but often the case is that the last questions in question 4, question 5, they are the harder ones in scholarship. And if you saw a system of equation that was in like question maybe 1 or 2 that was like looked similar, it's probably a bit more reasonable. But this one had that really sneaky trick about an arithmetic sequence. Like if you didn't notice that, then you could be going around for pages and pages making no progress. So please, in your Scholl exam, do not start on the last question of the paper. Yes, it's probably one of the harder ones. Yeah, that was a long video, but there was lots to get involved with. Hopefully you found it useful. See you in the next one.